In this chapter, we are going to discuss thermodynamics, which is the study of energy and spontaneity of the processes. We will look at different thermodynamic functions that will help us determine spontaneity of the process by looking at the entropy and also give free energy as well. This chapter is broken down into 3 different sections, and at the end of this chapter, my hope is that you will be master in this skill that listed on these learning outcomes. Throughout this chemistry course sequence, you have seen so many reactions already, and you might wonder what is a driving force that causing the reaction to proceed one way or the other. So in this chapter section, we will look at the factors that determine the spontaneity of the process. Please read the OER textbook chapter 17.1 for more details. First, let us differentiate between the spontaneous process versus non-spontaneous process. Spontaneous process occurs without ongoing outside intervention. Note that the key is without ongoing outside intervention or outside work or energy. However, for the non-spontaneous process would be the process that will occur with ongoing outside intervention or ongoing outside work or energy. An example of spontaneous process would be the candle burning. We consider candle burning as spontaneous process because when candle is burning, it happens by itself without ongoing outside intervention. Note that at the initial state, it may require ignition, but once it happens, there is no ongoing outside intervention. The reason why candle will require some ignition, this have to do with the kinetics. If you recall from Chem 122 for the kinetics section, you learn that for a reaction to occur, the molecule must collide with sufficient energy and with proper orientation. Without ignition, the molecule of wax and molecule of oxygen will not react because they both will not have enough or sufficient energy to collide to overcome the activation barrier. So the ignition is required to give enough energy to the oxygen and the candle wax molecule to be able to collide and also overcome the activation barrier. And once that reaction happens, as you see, the candle will burn without any ongoing outside intervention. Therefore, this process is considered to be spontaneous process. An example of non-spontaneous process would be biking uphill. The biker will need to continuously paddling in order to go up toward the hill. In this case, this process would consider to be non-spontaneous process because the biker will need to input ongoing work, because without doing so, then the bike would just roll downhill. Next, we will take a look at the difference between the speed of the reaction or kinetics versus the spontaneity of the process, which is thermodynamics. The kinetics terms are not the same as the thermodynamics term. Kinetics describe the rate of the reaction and it will tell you about how fast or how slow the reaction will proceed. It explains the effect of the concentration of the reactant on the rate, and also it explains the effect of the catalyst or inhibitor on the rate as well. Let's consider this reaction diagram here. This reaction diagram plots between the energy versus the reaction proceed or time. And we will start with the reactant. For the reactant, according to the kinetics theory, for the reaction to occur, the molecule of the reactant must collide with proper orientation and also with sufficient energy as well. This activation barrier is referred to the sufficient energy that the molecule of the reactant must collide and then convert into the product. And how the catalyst affect the kinetics is that the catalyst will lower the activation barrier by providing an alternative pathway for the reactant to proceed in order to reach to the product. Therefore, it can increase the speed of the reaction. In conclusion, the activation barrier would be the kinetics term that will determine the rate of the reaction. However, when we discuss about thermodynamics, we don't care how fast or how slow the reaction would proceed, because the only thing that we would look at is going to be the difference in energy between the product versus the reactant. The difference in energy between these two would tell us about the thermodynamics term. The thermodynamics term would describe the stability between the product versus reactant. It will also describe the spontaneity of the process and also the equilibrium of the process as well. The stability of the product versus reactant will tell us that at equilibrium, which one would be predominant. For example, if the product is less stable, which has higher energy than the reactant is more stable or has lower energy than the product, then at equilibrium, the reactant would be predominant because it's more stable. Similar to the spontaneity as well, the spontaneity will be determined from the stability of the two states as well. For example, if the product is less stable or have higher energy, then the reaction would most likely to proceed from the higher energy state to a lower energy state, similar to the flow of water that go from a higher position to a lower position. In conclusion, kinetics and thermodynamics are not related. In order to determine the speed of the reaction, we will need to look only at the activation barrier, versus if you want to look at the stability or spontaneity of the process, then you will need to look at the difference in energy between the product versus reactant. Here are the examples that show that the spontaneity and the speed are not related. For example, if you have ice cream, the ice cream at room temperature will spontaneously melt. And if you compare this with iron nail, if you leave the iron nail at room temperature, eventually it will become rusty. Therefore, these two processes considered to be spontaneous processes because they both will happen without ongoing outside intervention. Ice cream melt without ongoing outside intervention, and nail will become rusty without ongoing outside intervention. Therefore, again, these two will considered to be spontaneous processes. However, if you compare the speed of the reaction or the rate of the reaction, you will see that the spontaneous process of the ice cream melting would happen in a faster rate than the rusting process of nail. In conclusion, the spontaneity and the rate of reaction are not related. Spontaneity will not tell you about the rate of the reaction. Vice versa, the speed of reaction will not be able to tell you about the spontaneity of the process. Now the question is, what factor that will tell us about spontaneity then? We would first take a look at the change of enthalpy for the reaction. Thus, the change of enthalpy of reaction will always tell us about the spontaneity. We will take a look at the two examples that will help us answer this question. The first example is candle burning at room temperature. The second example is ice melting at room temperature. Note that these two processes at room temperature, it will occur spontaneously. Next, we are going to take a look at the change of enthalpy for these two processes. Consider the candle burning first. When candle is burning, it's going to release light and emit heat. Therefore, the change of enthalpy for this process would be negative, indicate that this process is exothermic. On the other hand, melting of ice, when it changes the physical state from solid to liquid, the solid will need to absorb heat in order to break down the intermolecular forces and become liquid. Therefore, the enthalpy change for this process would be positive, indicating that the ice cube will need to absorb heat, and this process therefore is an endothermic process. So if you look at these two examples, we see that both are spontaneous process, and one of them is exothermic and the other is endothermic. Therefore, the enthalpy change is not only factor that will tell us about the spontaneity, because both of them are spontaneous and one can be exothermic or the other can be endothermic. Therefore, in this case, the answer to this question would be no. The change of enthalpy is not going to always tell us about spontaneity. The next question is then, how can we predict the spontaneity of the process? We will take a look at these four examples in order to help us determine what is the factor that determines the spontaneity of the process. Note that from the previous example, we already see that the spontaneous process can either be exothermic or endothermic. And in this, for example, 3 of the example doesn't involve with the heat change of the reaction at all. Only the last one that involved with the heat change. Therefore, in this case, the first 3 examples will exclude the enthalpy change for the reaction. Let's consider the first example. When a drop of dye is added into water, what do you observe here? You will observe that once the drop is added to water, it will not stay at just one drop. Eventually, it will disperse throughout the beaker to mix and become a uniform mixture, and it happens spontaneously. Second example is this perfume. Imagine that if you spray perfume, the perfume will diffuse throughout the air and it will disperse throughout the room. Someone will eventually smell it. The reason for that is because the perfume is unlikely to concentrate in one spot. However, it's going to diffuse and then spread throughout the whole room. And this process happens spontaneously. The third example is when you have a balloon, and if you blow a balloon up and if you let go of that while the balloon is deflating, you will see that it's going to fly everywhere. The reason for that is because the air inside the balloon will not concentrate in there. It's most likely to come out and disperse throughout the air outside or throughout the container outside. And this process would happen spontaneously. You will see that the first, second, and third example of this process are spontaneous processes, and things that you can see in common is that they are going to have the dispersal of the matter that happened, or the matter will not concentrate in just one small place, but they are most likely to disperse throughout the surrounding. Now let's consider an example for TNT exploding. The explosion of TNT going from a high concentrate energy molecule TNT, and once it undergo explosion, it will then break up those bonds and then become more dispersed molecule that spread throughout the surrounding. In this reaction, it will also disperse the energy as well. This reaction not only disperses the matter, but it also disperses the energy. And once the TNT is detonated, you will see that both matter will become more dispersed and energy will also become more dispersed as well as it undergo explosion. All of these are an example of spontaneous process, and things that they have in common would be these spontaneous process involved with the dispersal of matter and also the dispersal of energy. And we can say that nature has tendency to mix and to spread out or become more dispersed. An easy example to understand this concept is think about your room. After you finish cleaning and organize your room, eventually your clean room after a few days, it will become messy again because it's going to spread out, and that's what the spontaneous process would be. However, in order to make your room to be organized again, that process would be non-spontaneous because you will need to input ongoing work to clean it up and put them together in order. So the spontaneous process would be the process that become more disorder of matter or energy, or more spread out of matter or energy. Because the dispersal of matter and energy is a driving force for spontaneity of the process. So we are going to take a look at each one of these. The dispersal of matter is related to the greater and more uniform dispersal of matter. For example, if you have gas sample, this gas sample is separated from the next flask by this valve right here. Once this valve is open, you will observe that the gas molecules will not stay as one side. However, it will travel spontaneously to mix and to disperse throughout the whole system. And again, this process is spontaneous because it results in a greater dispersal of matter. On the other hand, going from the greater, more uniform dispersal of matter to a more orderly of matter, this process would be non-spontaneous. Non-spontaneous process is not impossible. It is possible, but it just requires ongoing outside intervention. For example, you might need to somehow force this side of gas to go to the other side, and then eventually you will need to close the valve for the gas molecule to continue stay in one side of the flask. For the dispersal of energy, consider the two objects at different temperature. The dispersal of energy would be the transfer of heat from a higher temperature or a hotter object to a colder object. As the heat transfer, you will see that the heat will transfer from a more concentrated heat to a lower, less concentrated heat. Therefore, eventually, once they become in contact, the energy will disperse throughout the two objects, and this process would be a spontaneous process because the heat eventually will become more uniform dispersal of energy. Note that these concepts still need to follow the conservation of the energy because the heat will not be created nor destroyed. It's just the transfer between the two objects. And the take-home message for this chapter section is that 1. Spontaneous process happen without ongoing outside intervention. 2. Spontaneity is not related to the speed of the reaction. How fast or how slow the reaction is depends on the activation barrier, has nothing to do with the spontaneity. And 3. The dispersal of matter and energy will be used to predict the spontaneity of the process. If the system becomes more dispersed in matter and or energy, then that process would be spontaneous process.